Hello, everyone. I am today's session chair, Zhiqiang Wei from Xi'an Jiaotong University. This week, we will have the second lecture of this series talk on the evolution of physical layer communication waveforms. Today, we are very delighted to have Professor Zilong Liu from University of Essex. He will talk about the waveform of AFDM, a permission backwards compatible waveform for resilient and scalable 6G systems. And before the talk, please allow me to briefly introduce Dr. Zilong Liu. Dr. Zilong Liu is an associate professor, the 6G lab director, and the 2024 outstanding mid-career researcher in the Faculty of Science and Health, University of Essex, UK. His research generally lies in the interplay of coding, signal processing, and communications, with a major objective of bridging theory and practice. So far, he has made a series of original contributions to sequences, waveforms, and multiple access. He has widely published in high-quality journals such as TIT, TSP, JSAC, GSTSP, and Proceeding of IEEE. Prior to his current post, he was with Huazhong University of Science and Technology, Tsinghua University, Nanyang Technological University in Singapore, and the University of Melbourne, the Hong Kong University of Science and Technology, and the University of Surrey. And you can also to go to his website to find more details. And today he will talk about AFDM, a permission backwards compatible waveform for resilient and scalable 6G systems. And this talk will introduce AFDM, and also besides the basic principles, he will introduce a series of recent research advances on AFDM, including non-orthogonal AFDM, AFDM-aided sparse-coded multiple access, and MIMO-AFDM in the face of hardware impairments. And more importantly, a real-time lab environment USIB proof of concept implementation of AFDM against OFDM developed by 6G Lab of Essex will also be shown. That's very impressive. I'm very looking forward to it. So, Professor Liu, now it's your time.
Hi,
Yeah. I will stop the sharing, and you can share a slide.
Please. Yeah, please stop sharing. Let me share over. Thank you, everyone, for coming to my talk, and thank you, Zhiqiang, for your warm introduction. And so from title now you can see. So I'm going to talk about the waveform. Okay. And so before I formally start my talk, so I would like to ask everyone a question that, I mean, why we have so many people, who are doing the research on the waveform? Well, I think one reason is that so from 1G to 2G, and from the 2G to 3G, okay, and then from 3G to 4G, and then we have a same radical change of the waveform, okay, and also in fact the waveform actually lays the foundation of the physical layer system. So yeah, basically, I mean, a tiny change of the waveform for the physical layer, it actually means a lot of efforts for us. Okay, and so in this talk, I'm going to introduce you about the AFDM. Okay, so so some of you may have noticed that here I have actually changed my title, from the 6G to 6G and plus. So from what we heard from the current 3GPP is that and it's likely for the OFDM to be continued to be the major waveform for the 6G. So technically, for us, yes, we regard, I mean, the waveform design as a long battle. Okay, so basically from now on, we should not aim for the 6G, but we should also aim for the 7G. All right, and so my talk will be divided into 4 parts, and I will first introduce you about the
Hi, Professor Liu. Excuse
background.
me. Could you please share your screen to the, put your slides to full screen?
Oh, very strange. I'm actually using the full screen, actually. Just hold on for 1 second.
You need to share the table, remember?
How about now?
Yeah, all right, now. Yeah, great.
Okay, good. Yeah, so, and so I will first introduce you about the background. And so I will mention about our vision, the channel, and the basic principle of the AFDM, and followed by a demo. And then I will mainly introduce you 2 major works. One is on the non-orthogonal AFDM, and also on the AFDM and AFDM-SCMA. And so finally, I will conclude this talk with a number of future works. Okay, and so so I will mainly introduce you the first 5 paper, and let's say we have time, I will also slightly introduce you the last 2 paper. Okay, so from the 5G to 6G, and we are supposed to further push the limits of the wireless system design in terms of a number of the KPI, and so, for example, in terms of the spectrum efficiency, in terms of the latency, in terms of the collection and density, and also about the mobility. And so in this paper, we have a survey the chirp-based OCDM and AFDM for 6G and beyond. And so in the picture now you can see that actually the 6G and beyond networks are supposed to support reliable communication over highly dynamic environment. And so in terms of the communication with the satellites, the communication of the NTN and TN. Okay, so and so from the UK point of view, so our the view for the 6G is that it will be more about the resilience, scalability, and the sustainability. Okay, and so in last talk, by Shuangyang, he has already introduced you about the channel. Okay, so basically a major challenge for the current waveform design is that we need to deal with the time varying multiplexing and channel. And so basically let's say here, and we send out a single tone, but actually because of the mobility, and then so the spectrum will become spread, okay? And we call it as Doppler and T-spread. And also from time to time, now we can see the change of the channel, okay? So so in the past few years, and we have seen numerous research, look into the delay and Doppler domain communication, and so for that one, we have the multi-carrier OTFS and the ZAC OTFS, and ODDM and OTSM, okay? And so the basic idea here is to send out our data symbol, through the delay and the Doppler domain, rather than the time and frequency domain. And so the key idea here is to use a kind of a 2D transform, and then through such a 2D transform, and then we are able to spread every symbol, in the delay and the Doppler domain into the time and the frequency domain. And I personally, very much like, the delay Doppler domain communication. And so the main reason here is that we can see a strong sense of the beauty, and behind, okay? But from the recent 3GPP meeting, however, we heard that, OTFS, may be less likely to be selected for the 6G, okay? And so the question here is that what sort of a waveform do we need for 6G and 6G and beyond, okay? And so here, from my point of view here, I have summarized a few points here. And so first of all, so we wish to see an evolving 6G and beyond. So meaning that, so in fact here, it's very essential for the waveform, to have a strong backwards compatibility to the conventional OFDM. And secondly, we wish that, such a waveform should have a strong resilience to the dynamic wireless channel and then hardware impairments, okay? And thirdly, and we wish to find a waveform, which is able to achieve a large diversity order. And remember that for the multi-carrier OTFS, in fact, we can only achieve the diversity order of 1 in the higher single region, okay? And so we also wish that such a waveform should have a very high flexibility, for the support of very diverse use cases and the QoS requirements, okay? And also, in view of the 6G, we are also such a waveform should also be able to support the joint sensing and communication called ISAC, okay? And seamless integration with MIMO and support the highly secure communication, okay? And lastly, which is a very and lastly and importantly, we wish to see a waveform, which is not heavily patented, I mean, by a single company. Okay, so meaning that actually, so the selection of the 6G waveform, will be based on a wide range of the consensus. All right, let's say if one or two company, so they own a majority of the patents. So in fact, it will be hard for us to push it into the 6G. Okay, so based on the question and in the previous slide, so and so in the paper below here, we have actually considered the so-called multifunctional chirp signaling for the next generation multi-carrier system. Okay, and so the key point is to look into the chirp signaling. Okay, in fact, we have already used the chirp, for the radar sensing, and in the 4G and 5G, we have actually widely used the ZC sequences, for synchronization and channel estimation. Okay, and also in LoRa, we have actually used the chirp spectrum to transmit communication data. Okay, so based on that, now in fact, in 2023, and so Annie in France, so they published the paper below in Bolton, called affine frequency division multiplexing AFDM. And so the basic idea of the AFDM here is to modulate the data over the orthogonal chirp, the subcarriers. Okay, so using the inverse DFT. Yeah. So here now you can see the transmit signal here, and so and here now we can see the C1 and C2 as the two parameter here. All right. So basically, by setting the C1 equals to C2, now we can see the entire AFDM will reduce to OFDM. Okay, but here now you can see, so basically here, the C1 will actually control the chirping rate in the time domain. Okay, and the C2 will in fact will control the chirping rate in the frequency domain. Okay, so basically the key idea of the AFDM, although was published in 2023, in fact, we before that, in fact, we also have the chirp of the OFDM and also the fractional Fourier transform based on the multicarrier and the AFT based on multicarrier, and also the OCDM in 2016. Okay, and so finally, we can also look into the time frequency representation of the AFDM and OFDM. Okay, so in OFDM now we can see that in fact, so the data symbols are multiplied through the multiple orthogonal subcarrier. Okay, but here in the AFDM, in fact, so the data symbols are modulated through the orthogonal subcarrier. And so here now you can see that every symbol will be spread in the time and frequency domain. Okay, so now here now we can see that, and from the transmitter point of view, so we can actually to implement the AFDM through the minimum change of the conventional OFDM. Okay, so the AFDM in fact has a strong backwards compatibility to the conventional OFDM, and also here because of the time and frequency domain is spreading, so the AFDM in fact has a strong resilience to the Doppler CFO phase noise, and also can achieve the full channel diversity. And thirdly, because of the chirp signaling nature of the AFDM, so the AFDM in fact is born to support ISAC. Okay, and also by controlling the parameter of C1 and the C2, we are able to achieve the highly flexible and secure communication. And so in the paper below, we have actually studied the MIMO-AFDM in the face of the hardware impairments, and such as the DC offset and the DC low resolution DC, and the IQ imbalance, and the nonlinear PA, and the phase noise. Okay, so here now you can see, so based on the setting here, and then by following the setting of the skin 1, now we can see that the AFDM channel matrix here, now we can see that all the multiparts, can be well separated. Okay, even giving all the hardware impairments. Okay, and also here, in this paper, we have actually studied the impact of the CFO here. Now we can see for the conventional OFDM, let's say we have a CFO of 4%. Now we can start to see the error flow. Okay, but now once we have the CFO of the 8%, now we can see a high error flow. But here, for the AFDM, now we can see that even for the CFO of 8% of the subcarrier spacing, now we can see we are able to achieve BR very close to the case with the ideal hardware. All right. and so also here we compared the performance of the AFDM and OFDM and for the different velocity under the 5 types of the hardware impairments. Now we can see that so giving the DC offset and the IQ imbalance and the no resolution of DC and power and the linear PA, now we can see that actually AFDM consistently outperform. Okay, and so finally here we compared the CISO OFDM and the CISO AFDM, and so now we can see without all the hardware impairments, now we can see the AFDM in fact can achieve 14 dB gain for the BR of 10 to the power -4. And also here now you can see that even with the hardware impairments, so the BR of the OFDM was saturated, at 10 to the power -3 here. But actually, for the AFDM here, now we can see, so the BR, has a floor of around 10 to the power -5. Okay, so this actually shows that, really, the AFDM not only outperform the conventional OFDM for the high mobility channel, but also, by considering a number of hardware impairments, in fact, we can see the AFDM, is much better. Okay, and so here, I want to show you a demo, and basically, it's a real-time lab environment, the proof of concept and the demo of the AFDM. Okay, let me play it. Let me show how. Just hold on. All right, no, let me play it. Okay, now here, so we send the AFDM and OFDM in TDD mode. Okay, and so we send then using the same power, and now we can see. So we set the gain to be 6.2 dB. Okay, now here is the transmitter. Now we move to the receiver, and we turn on it. And so from here now, in the beginning, so we see a lot of rubbish data, but now, and soon now we can see the constellation now becomes stable. Okay, but here, by looking into the constellation of the AFDM and OFDM, okay, now we can see AFDM actually has much tighter constellation. Okay, now we can move on. Now we can move on, continue, and so next, and what we do here is that we reduce the transmit gain to 56. Okay, now and once we reduce the gain, now we can see that really, now we can see here. So really, I mean, the OFDM is struggling and to recover the transmitted images. All right, but actually, for the AFDM now you can see. I mean, although the constellation becomes worse, but actually, we are able to fully recover the picture. Okay, now we can see it. Now we can see it. Yeah. Okay, now moving back and to the transmitter side again. Now we further reduce the gain and to 50. Okay, we further reduce the gain to 50, and so in this case, since the gain is too small, and so we are both AFDM and OFDM are not able to recover. Okay, but now, once we return to the previous gain of T62, now we can see now the demo now return to normal. Okay, yeah, so this actually is actually our demo. So now let me move to the first major result, on the non-orthogonal AFDM for highly spectrum efficient communication. And so we know that for the conventional OFDM, so the requirement here is that all the subcarriers should be fully orthogonal, okay? And so in the paper below, and they have actually proposed the so-called SE-FDM, okay? And so the key idea here is to compress the spectrum, and by introducing a compression factor here, okay, so by doing so, now we can see the the compressed his subcarrier are not orthogonal, okay, and so in that case now we can see our transmitter and our receiver, okay, and so in this case now we can see our transmitter and signal in fact now becomes a function of the compression factor alpha, okay, so meaning that in the transmitter side we have purposely introduced an ICI, okay, and so now we can see our receive signal here, and now we can see that it is also a function of alpha, all right, and so here now we can see, I mean, once we so here once we compress the subcarrier, now we can see from the channel matrix side, now we can see in fact it is also a function of the alpha, okay, so the major problem here is that so now we can see the energy leakage, okay, for the channel matrix. So in fact here it may affect the final performance here, all right. So and in this paper, and we have actually and we pioneered the concept on the non-orthogonal AFDM, okay, and so here we consider a hot decision based receiver. Now we can see now we can see the conventional AFDM under the linear MMSE receiver, and for the OFDM here now we can see that we have so here we see a big gap here, but here now we can see for the conventional non-orthogonal AFDM, even with the alpha equals to 2.9, now we can see the BR here is actually very close to the conventional AFDM, okay. And so in the paper below, so we proposed a soft iterative receiver for the non-orthogonal AFDM, and so here so the basic idea here is that here we first carry out interference cancellation, and the soft symbol clipping, and the error calculation, and the symbol decision, okay. So here we will calculate the mean and variance, okay, and also and so after the stage 1, and then we so we move to stage 2, and so here I mean since we have already calculated all the variance of the different symbol, okay, so here so we first so we do a variance sorting, okay, so and so the basic idea is those symbol with a large variance, are regarded as less stable. Okay, and so in that case, I mean, what we do is that so we can to select a few symbol with large variance, and then we carry out the symbol-wise ML detection. Okay, and so here now you can see that in the receiver side, and before we carry out the soft iterative detection, here now we can see that here we have one module here, which is called the magnitude-based ICI pruning. And so the basic idea here is that so we look into the channel matrix. All right. So by looking into the channel matrix here, now we can see that we are able to to prune, the channel matrix. Okay. So let's say here, so when we consider the pruning value of D to be half of the sequence length, or let's say to be 1/4 of the sequence length. Now we can see that actually, we are able to to achieve the low complexity receiver design. And so here now we have compared the encoded BR here, and so now we can see the non-orthogonal AFDM here. Now you can see that so by comparing to the OCDM, we are able to achieve over 10 dB gain for the BR at 10 to the power -4. Okay, and also now we can see a larger gain, compared to the conventional OFDM and the SC-FDM. Okay, and so finally here, and we compared decoded BR. Okay, and here we consider the rate of 5/6, and alpha equals to 0.9. Okay, now here, and by looking into the purple line here, now we can see LDPC coded AFDM here. All right, so but now in fact here now we can see for the LDPC coded also AFDM here. Now, in fact, so when alpha equals to 0.9, we are able to achieve BR very close and to the coded conventional AFDM. Okay, and also comparing to the conventional OFDM here, now we can see that we are able to achieve the gain of 3.2. Okay, and so now let me move to the AFDM-SCMA. Okay, and so the purpose here is to achieve the massive collectivity over the high mobility channel. And so here now we can see that for both the 5G and the 6G. Okay, and one important objective is to support the massive collectivity. So so for that one, in the past few years, we have same numerous paper on norma. Okay, but in fact, from the industry point of view, in fact, it is more promising for us to consider codomain norma. So the reason here is because here we have seen a huge the success for the conventional CDMA. Now, actually, by moving from the CDMA and to the codomain norma here, now we can see the many types of codomain norma scheme here. Okay, and so in this work we have actually looked into a promising codomain norma, which is called the sparse code multiple access, and so the basic idea here is to divide the frequency and domain into multiple blocks here, and now we can see that for the block 1, and then we have a 4 subcarrier, right? So now you can see that over this 4 subcarrier, we are able to support the 6 user. Okay, so here now you can see that we are able to achieve the overloading factor of 150, and so now, and here now you can see how the encoding is carried out, and so the key idea here is to design some sparse codebooks. Okay, and so in the paper below here, yeah, so we consider the BR performance of the OFDM based SMA. Okay, now here now you can see that giving the CFO of the 2% here, now we can see a major airflow here, and then once we move to the CFO of 4% or 6%, now we can see a higher and higher airflow. Okay, so in fact here, actually it means that we are not able to support SMA in high mobility channel. And however, I mean, for the SATA IoT or for the V2X, yeah. So in fact, for a lot of the scenario, and yeah, so we need to deal with I mean, how we're able to support the massive collectivity over the high mobility and channel. And so in this paper we have actually consider how we're able to combine AFDM and the SCMA. Okay, and so the basic idea here is that so we will use the SMA to support the massive collectivity, and then we will use the strengths of the AFDM, to combat the high mobility and channel. Okay, and so here now you can see, and what we do is that we will first carry out the SMA encoding, and then after that, so we place all the SMA code words, in the DFT domain, and we consider 2 types of the transmission. One is the localized the transmission, and also the interleaved the transmission. Okay, and so here in this examination here, we have compared the encoded BER with the conventional OFDM. Okay, so now we can see that so by giving the AFDM, now we can see that we are able to achieve 10 dB gain here. Okay, and so further, here we we have consider a new type of receiver here, in terms of coded AFDM-SCMA, and so for that one, we have the conventional receiver without any outer iteration, and we also have the turbo receiver. Okay, so here we consider a new type of receiver, which is called an OMP. Okay, and so for those of you who are interested in OMP, you may look into the paper here, and so from here now you can see the both the OMP based receiver and the turbo receiver, in fact, are very similar. Okay, so the only the difference here is that here, and in OMP and based receiver here, we need to calculate the value of B gamma and B phi. Okay, and so comparing to the turbo the receiver, where the value of B gamma and B phi equal to 1, and so basically here, and so for us to use the idea of the OMP, in fact, we will need to consider a system, with a nonlinear transform, and then followed by a linear T transform. Okay, and so by moving on, and so our key idea here is that so our key idea here is to consider a new type of SMA codable design, and in such that we are able to express the SMA encoding as a linear transform. Okay, so by looking into here now we can see that for the entire SMA encoding and the AFDM modulation and the channel, so we are able to express it as a linear T transform. Okay, and so in that case, by considering the LDPC coded AFDM-SMA receiver, now we can see we were able to regard the LDPC encoding as a nonlinear transform. Okay, and so here, since we are able to combine the SMA encoding and AFDM and modulation channel to be a linear transform. Okay, so this actually allows us to use the OMP. Okay, so now we can see that we can see the performance here, and so first of all, when we compare the AFDM based and once we consider the OMP based AFDM with the conventional turbo, okay, now we can see that we are able to achieve 4 dB gain, and also by comparing with the OFDM, now we can see we are able to achieve about the gain of 2 dB. All right, and also for the uplink, now we can see a similar trend here. And so finally, so in this talk, I have introduced you the basic principle of the AFDM, and I have shown you a demo, and I have shown you that actually, the AFDM, is very resilient to both the high Doppler channel and also the hardware impairments. All right, and I have also presented the non-orthogonal AFDM and the AFDM-based SCMA. Okay, for the future works, and so I believe that we have a lot of new idea and the new directions. All right, and so for example, how we're able to have a unified framework, for all the current 6G waveform. All right, number one. Number two is how we can see that AFDM can be used for the highly secure communication, and how we can study waveform existence of AFDM and OFDM and then OTFS. All right, and how we can design AFDM AD ISAC, and how we can apply the AFDM for the optical wireless communication, and how we can to really carry out the trial and then see the standardization of AFDM. All right, and so finally, since we have a small amount of time, so I want to say some words, on the generalized spatial modulation based AFDM here. So the basic idea here is that so for every symbol transmission, so we only activate a few RF chain where the symbols here, and here, so we carry out the AFDM encoding. And also in this paper, we have designed the JP-based AFDM, and so here, the major idea here is that instead of using the CP-based AFDM or the CPP-based AFDM, here we have actually used zero padding here. All right, so now we can see that once we use the zero padding, now we can so the time domain channel matrix here, now we can see a sparse and lower triangular and channel matrix, and such a property allows us to carry out a low complexity and receiver design. All right. Finally, now we can see we have published many paper on the AFDM, in the past few years. And so finally, I want to make use of this opportunity and to thank my founder and my collaborator here. And so, yeah, okay, thank you.
Thank you, Professor Liu, for your excellent talk, comprehensive introduction on AFDM and some research advances.
Yeah.
That's great. We have several questions from the audience, and I will select several of them. And first one is, how AFDM different from OTFS? Is AFDM more resilient than OTFS in NTN?
And okay, so for me, and to answer such a question, let me go back to here. All right. So in fact, for the conventional multi-carrier OTFS, right? So in fact, we can actually to prove that in fact it can only achieve a diversity order of 1 in the higher single region. Okay, so from that point of view, actually the current AFDM is much better than the conventional multi-cable based OTFS. Okay, and however we have so we also have the ZAC based OTFS. All right, and here we have same sandpaper which actually shows some point of the equivalency between the AFDM and the ZAC-based OTFS. Okay, so for that reason, in fact, so some paper, kind of also regard the AFDM, as a kind of a delayed Doppler waveform. Yeah. So I would say that at least from the transmitter point of view, now we can see. So actually, we are able to design the AFDM, through the minimal modification, based on the conventional OFDM. Okay. So and also here, we have studied the AFDM, in the face of the hardware impairments, and so we believe that by considering all of that, so AFDM can be a very promising 6G waveform. Yeah, thank you for the very good question.
Thank you, Professor Liu. And the second question go to the coexistence of AFDM with other waveforms in 6G or 6G plus, maybe.
Yeah.
Let me see. Regarding the unifying framework and the coexistence you mentioned in your future work. So considering 6G will likely to be a heterogeneous network. So you foresee AFDM being an on-demand fallback for OFDM specifically triggered in high mobility scenarios? Or does this unified framework imply that the future transceiver will seamlessly switch between these waveforms within the same frame by simply tuning some waveform parameters?
Oh, yes. And I hope so. In fact, here you can see, and I do agree, 6G, will be a highly heterogeneous network. Okay, so by considering integration of TIN and NTN, for example. So sometimes we need to support, several low mobility user, and then sometimes we need to support some high mobility user. And so in that case, our vision is that maybe here we are able to use the AFDM, which to generalize, the OFDM and the OCDM. So basically, by only configuring, the parameter of C1 and C2, and then we are able to handle highly complex use cases. Yeah, thank you.
Yeah, I agree. The adaptability and the flexibility of AFDM is I think is a big benefit to like a coexistence with other waveforms or adapt to the network.
Yeah, that's right. That's right. Yeah, yeah.
And the last question, To be honest, I cannot fully understand these questions. I can read it for you to see if you can understand.
Okay.
In the continuous time AFDM model, the instantaneous chip frequency is folded within the sampling frequency. I'm not sure what's the sampling frequency. Maybe it's bandwidth. But discrete symbols can be directly mapped to a continuous time signal. His question is whether this frequency folding is truly necessary.
I don't know, in fact. Yeah. So and so personally, I regard, the AFDM as a kind of the time and frequency domain is spreading. Okay, maybe I will go back to here. Maybe I will go back to the beginning, to here. And so I personally, I regard, the AFDM, as a kind of the time and frequency domain is spreading. Okay, so and my vision is that we should have some other on modularic and the time and frequency domain is spreading. Okay, and so and my feeling is that we should kind of more look into such a problem, from the precoding point of view. But of course, necessarily we want to really to make use of the AFDM for sensing, right? So in that case, we may need to see some continuous waveform, for sensing. And so for that purpose, necessarily we want to use the AFDM for sensing. And my personal opinion is that we need to first tune the chirp rate first, okay? But then, once we are able to tune the chirp rate, so then it means that we will have a more constrained, the spectrum wrapping. Yeah, that's my idea.
Thank you, Professor Liu. I think I have read all the questions from the audience, but for me, I have some personal questions.
Okay, thank you. Thank you.
Yeah, I want to ask some fundamentals of AFDM. First is a chip-based waveform, and it is swapping between the bandwidths. I'm wondering, where is the sparsity come from? Why the effective channel in the affine frequency domain has a sparsity?
And so here, in the last part, okay, I have in fact I have actually mentioned that. So we saw some paper, and they actually they have shown the equivalence, between the AFDM and the ZAC-OTFS. Okay, so somehow they regard the AFDM as a kind of delay and Doppler domain waveform. Okay, and so because of that, and then so you kind of also by considering the sparsity of the delay Doppler channel. Okay, so here we can see that so we have some sort of sparsity here. Yeah, so and my personal understanding is that we should look into the unique equivalence, between the AFDM and the Zycle GFS, and so then we're able to look into it, from the delay Doppler domain waveform point of view, and then so we will see the sparsity.
But a further question is, because you're trying to resolve a multipass.
Yes.
No matter what domain it is.
Yeah.
If it is follow up the framework of OFDM, where does the high resolution come from? Particularly in the Doppler domain.
Yes, very good question, Zhixiang. Okay, and so from here now we can see, and in the time domain, so basically we may regard the time domain signal, to be the product of the OFDM time domain signal and a chirp sequence. Okay, and so we know, in fact, for the chirp and sequence here, let's say here, and we send out chirp and signal. All right, so the chirp, in fact, is very good at so the reason is we are able to achieve an ideal, the autocorrelation side lobes. All right, and even in terms of the aperiodic autocorrelation, in fact, the chirp sequence, has very good performance. Okay, so my understanding here is that let's imagine that we spread out our data sample over several chirps. All right, so once we spreading out over several chirps, and then at the receiver, sees the chirp sequence has very good the autocorrelation. All right, then we are able to to separate the then out, between the multiple passes. Yeah, that's my understanding, from the sequence angle of the chirp. Yeah.
Okay, thank you very much for your detailed explanation. And I think that's all the questions, and we can complete today's session. Thanks, Professor Liu, again for your excellent talk and detailed explanation to the questions of the audience and me as well. Thank you very much.
Thank you, Zhixiang. Yeah, thank you so much for having me. Thank you. Okay, bye-bye. Yeah, have a nice day.
Bye-bye. Yeah. Have a nice day. Bye.
Yeah.